Welcome to our education series presentations. My name is David Elmo, and I'm a professor of engineering at the University of British Columbia. In this video, we will discuss a very important topic, that is the quantification of the Geological Strength Index, or GSI. I would like to thank my co-authors, Beverly Young, Tia Shapka-Fels, and Luca Zorzi for their input and comments. This is not a standard presentation. We have opted for a different format, one that involves telling a story, intercalating technical slides in between. As the title suggests, it is a creative and thought-provoking story about the many GSI quantification attempts available in the literature. We hope you enjoy our story. The Alchemist Lab, a creative and thought-provoking discussion about the quantification of GSI. The Alchemist Lab was a global community devoted to the study of rock engineering. The alchemists were proud of what they had created, despite any of those external observers offering criticism about their resistance to change. One of their major achievements was the use of classification systems, particularly GSI, a qualitative classification system the alchemists used to design tunnels and even slopes. However, many in the alchemist lab remain unfamiliar with the origins of GSI. Decades ago, an article appeared in a news journal that suggested that GSI is equal to RMR 76. For those not familiar with the terminology used by the alchemists, you should know that RMR 76 was an early qualitative classification tool introduced in 1976. RMR 76 considered 5 classical elements: interrock strength, fracture spacing, RQD, joint condition, and water, mixed to define a rock mass quality. Quality, not quantity, one voice could be heard saying from inside the lab. Indeed, the alchemists were not familiar with the differences between scales of measurement, and their calculation they continued using qualitative assessments as if they were quantitative measurements. The master ways to transform experiential correlations into mathematical equations, which gave the findings a neuroscientific validity. Curiously, another group of alchemists preferred using a subsequent version of RMR, and they believed that GSI is equal to RMR 89 minus 5, arguing that the minus 5 correction had to be included because of the way they considered the impact of water. The alchemists were not concerned with the reasonable deduction that the validity of both correlation leads to the incorrect statement that RMR 76 is equal to RMR 85 minus 5. Later, the alchemists had got accustomed to determine GSI using only 2 of the previously mentioned elements and referring to a simple diagrammatic table. The question as how the alchemists were now able to synthesize GSI from just 2 of the 5 known elements remained unanswered. The alchemists knew not to ask difficult questions about GSI and other empirical tools at their disposal, as they live in fear of the validation oracles. Let's pause the story for now. We heard that GSI was introduced in 1994 as an article in a news journal by the SRM, International Society of Rock Mechanics. In said article, it was assumed that GSI was equivalent to RMR 76, or alternatively, GSI was equivalent to RMR 89 minus 5. The table on the left is the first depiction of the GSI table. The numbers are RMR ratings under dry conditions. The table on the right is the one that followed in 1997. Note that the numbers in the cells highlighted in yellow in the table on the left correspond to the maximum ratings permitted in the cells shown on the table on the right. Also, the 1997 version includes massive and foliated groups not originally present in the 1994 version. But it is reasonable to conclude that the numbers in 1997 version still represent RMR ratings under dry conditions. We know that RMR is given by the sum of the ratings corresponding to 5 elements: interrock strength, RQD, fracture spacing, jointing condition, and water. Here we are using RMR 89 minus 5 equal GSI as a discussion point, but the same conclusion would apply if using GSI equal RMR 76. Now, when we look at the 1997 GSI table, the only elements being considered are the rock mass structural characters, vertical axis, and jointing conditions, horizontal axis. Therefore, if indeed the numbers in the GSI table are equivalent to RMR 89 minus 5, then we will need to conclude that those numbers must include a constant that represents the contribution of the RMR ratings for strength and water. However, as we will see in the following slides, none of the proposed quantification methods recognize the role of this constant. Indeed, one particular quantification method assumes that GSI is the sum of 1.5 times RMR ratings for jointing condition and RQD divided by 2. Clearly, we cannot equate the initial GSI formulation, GSI equal RMR 89-5 or GSI equal RMR 76 to the proposed quantification method, as by doing so we will not be able to balance the two equivalences. Later we will see many more of these equivalences, or as we call them, accidental functions. However, the problem of not being able to equate the different GSI quantification methods has so far been ignored by the engineering community. In the story, we also mentioned the problem that the alchemists in their calculation continued using qualitative assessment as if they were quantitative measurements. Are rock engineers familiar with the differences between scales of measurements? The measurements, inverted commas, we use in rock mass classification systems are nominal or ordinal. Therefore, they are qualitative assessments. The implications are twofold. First, how can we quantify GSI? That is, how can we transform GSI from a qualitative assessment into a quantitative measurement when the parameters we use in the so-called quantification process are themselves qualitative assessments? And second, we need to stop applying statistical function to qualitative assessments such as GSI, RMR, and Q. There are no such things as a mean standard deviation for GSI. Let us continue with the story now. We just introduced new characters, the validation oracles. Like the old scene of Sauron, the validation oracles guarded the discipline of rock engineering and believed that validation was required for all new formulae and methods being proposed. However, the oracles maintained that the old formula did not require further scrutiny. All formulae, they insisted, are validated by the continuous use. Apparently, the oracles had a different understanding of what constitutes scientific validity and used the term validation and calibration interchangeably. What about mechanism? Raised a voice in the lab. But the alchemists were more concerned about calibrating the models to observe the formation rather than focusing on mechanisms. The alchemists were not expected to question old formula or to read about the development in the old books. The oracles never asked the alchemists to share the full data sets, and the alchemists obliged them by distilling data in ways that would support the conclusions. The few alchemists that would dare to challenge the system were confined to the dark corners of the lab, the work either not published or simply ignored. Nonetheless, the original method used to obtain GSI was simple, and the results sufficiently precise. But the alchemists never seemed to agree on which GSI value to use. It is GSI 71, no, it's GSI 72. I tell you, it must be GSI 74, as if it were possible to tell the difference between a GSI of 71 and GSI of 74. They eventually started searching for ways to modify the original GSI formula, claiming that the old formula was too subjective and that a new method was needed to help inexperienced alchemists to accurately estimate GSI results. To better understand the story, one must know that the alchemists interpreted the term accuracy and quantity differently from the rest of the scientific community. The alchemists decided to name their revision efforts as GSI quantification. Some alchemists offered changes to only one element in the GSI table, others changed both elements, but the suggestion still involved using elements that were either too subjective or impractical to find. It is called GSI quantification, they argued, and is all that we need for the process to be considered objective. Time for another technical pause. Let's talk about calibration validation. What can we learn from history and philosophy that applies to rock engineering? You may be familiar with the geocentric model, which for almost 1400 years was used to predict planetary motions. And it did that reasonably well, despite the wrong modeling assumptions. Enter Copernicus and his heliocentric model. It did not significantly improve prediction of planetary motion over the geocentric model, but it certainly broke away from a dogmatic view of our universe. Note that both models are mechanically wrong. Neither Earth is at the center of the solar system, nor the orbits of the planets in the solar system are circular. The models therefore cannot be considered to be validated. Note that when Galileo tried to assert the use of the heliocentric model over the geocentric model, the Spanish Inquisition did not take it well. In a way, the validation oracles in our story do just that. They oppose views that contradict the rock engineering dogma. What lesson can we learn that apply to rock engineering? First, do not assume that your model is mechanically correct or validated because it matches observation. And second, the calibration made on the basis of fitting model results to observation does not necessarily provide an explanation about mechanisms. How can we quantify something that we cannot measure? That is the key problem with the different GSI quantification methods. Can the quantification GSI really make it less subjective, less dependent on experience? No, it cannot. Either rock mass quality is a physical property, and therefore GSI quantification is independent of experience. We just need to find the right tool to measure it. Or the estimation of GSI's values is indeed based on experience, in which case the rock mass quality is not a physical property, and GSI remains a qualitative assessment, which we cannot measure. Time to go back and meet our alchemist again. Some alchemists proposed to quantify GSI using the old RQD element, which was known to change its value depending on the direction on which one was looking at it. The origins of RQD could be traced back to the dark days of the Cold War and the use of an almost mythical 10 centimeter threshold. RQD, like many other formula, had endured the test of time. The test of time does not imply scientific reproducibility and validation, screamed the same voice deep in the lab. But the alchemists kept ignoring this voice. They all exclaimed, "Success, our new GSI formula validated." Indeed, the validation oracles did not pose many questions. Some say the oracles were absent from the lab while this new formula were being proposed. Others believe that since the new formula did not question the old books and even embrace the old RQD element, then the oracles had no interest in intervening. Oh well, even the mighty eye of Sauron may be nearsighted at times. The lab kept filling up with books with new GSI formula, but none of these books got used much, except maybe by the alchemists who wrote them. One day, several brave alchemists decided to open all the books, old and new, and to compare all the different GSI formula. They found that all the formula claimed to produce the same GSI result. What kind of extraordinary tool is GSI, they concluded. They can be created in so many different ways. The brave alchemists had stumbled across the homogenization secret of classification tools, which transform fractured rock masses in continuum media using a single value. Oh wait, isn't that a problem? Exclaimed the brave alchemist. But they could not even finish the sentence before the oracles quickly branded them as evangelists and asked them to validate the findings. These alchemists had not proposed a new method, they simply reviewed the old GSI method, a new quantification formula. The oracles clearly did not realize the contradiction of actually asking for a validation of the original GSI. And here they are, many GSI equivalences. Note that it's not possible to compare the different equivalences to each other without creating contradictory results. And there are actually some equivalences where the difference is only the RQD divided by 2 and RQD divided by 3. So how can basically now these two be equal? Many GSI tables. Are all these correct? And if they do provide an estimate of GSI that is not different from the one engineers will get with the original GSI table, why we should use them? Let's conclude our story. The brave alchemists concluded that the new GSI formula did not make any improvement to the quality and accuracy of GSI, and questioned how the new formula made any difference when no one, not even the oracles, could ever measure GSI. It is not a physical property, it is just a qualitative interpretation, and there is no need to quantify GSI. Just accept variability in your engineering design, they concluded. This is the end of the story, but it's not the end of the presentation. Clearly, the quantification of the original GSI table produces a condition by which engineers seek unique GSI values, not to mention unreasonably quoting GSI values with decimal precision. There is also the issue of the many quantification attempts using parameters that are either qualitative, for example, jointing condition factors for RMR or RMI, or not directly measurable in the field, for example, persistent factor. And more importantly, so-called validation of these quantification attempts show that there is no point to quantify something that is inherently variable like natural rock masses. Here, for example, the authors use a GSI plus or minus 10 as a validation range. We discuss now the problem model acceptance and model validation. That is, understanding how the validation oracles work. Let us consider an imaginary rock mass quality index from very poor, 0, to very good, 100. It is just an imaginary index. We want to publish our new findings, but we decide to neither provide details about the lithology, we just list generic rock types. Nor we indicate whether the data shown below represents average along boreholes. We use correlation to different parameters as validation tools. See the y-axis on both figures, they are not the same parameters. But in the figure shown on the left, we decide to arbitrarily drop data from 5 out of the 11 sites, including our database, because we want to reduce data scatter. Basically, we want to make our data more presentable. Is this an acceptable approach? Yes or no? Let's pause for a few seconds for you to think about this. Here is a surprise for you. Remember when the story we said that many in the Alchemist lab remain unfamiliar with the origins of GSI? How many of you have ever seen these charts before? These are the data used to justify the 10 centimeter threshold in RQD. If you answer no in the previous slide, then clearly you should not be happy with the approach used to justify the 10 centimeter threshold in RQD. And we know RQD has been used for many years, therefore it works. But does it really? Why do we accept RQD many limitations, but then require new method to adhere to stricter stability criteria? As we said in the story, invoking the continual use of empirical methods as evidence of its validity does not constitute validation. Let's have fun with quantum mechanics now. We here propose using the Schrödinger cat experiment applied to rock engineering knowledge. We need to accept the fact that in rock engineering practice, the term validation does not always carry true scientific meaning. Calibration does not imply validation. We can easily predict the past by back analysis, but validation of a forward model is something that we are not very good at, or we just don't do altogether. In rock engineering design, we do not truly build tunnels and slopes, we excavate them. That is, the design process is generally completed before we have access to rock exposures. As mentioned in earlier presentations about rock bridges, we could think of rock exposures as curtains, behind which there is no reality, only the potential for the reality. When it comes to RQD, replication will be the key to claim its validity. Until we find a way to perform a scientific validation, we could therefore think of RQD as being equally correct and not correct. Enduring the test of time does not imply scientific validation. And yes, the validation oracles are not infallible. Here we have an experiment in which 3,300 researchers were asked to review the same paper, jointly written by a Nobel laureate and an early career research associate. The data clearly showed evidence of review bias. While only 23% recommend the reject when the Nobel laureate is the only author shown, 48% do so when the paper is anonymized, and 65% do so when the early career research is the only author shown. How many papers in rock engineering journals suffer from this very same biases? How many manuscripts have not been published because the authors were not famous? Cognitive biases and human factors apply to engineering as much as they apply to economics, like in this case. We are not immune to them. Finally, we believe we should not stop introducing new GSI quantification methods and just going back to the qualitative GSI. Here, for example, we have reinterpreted the 1997 GSI version using data from Marinos and Cartes and Yang et al. To create a qualitative GSI table that embraces variability and accounts for geological trends. Note that the GSI ratings are reported as GSI plus or minus 5. In conclusions, we should not underestimate challenges related to empirical habits. Some engineering methods are constrained by practices that have emerged over the years in relation to personal and even national preferences. There is no such thing as accurate GSI or RMR or Q for that matter. Accuracy is defined with respect to an expected value, which is unknown to us since classification systems are not measurements of a physical property. Why are we afraid of variability? Why we cannot accept describing the GSI of a rock mass as, for example, 60 plus or minus 5? Remember, rock engineering design is like building a plane as you fly it. There are no prototypes. These are the references cited in our story. And thanks for listening. We welcome your questions and comments.